Today we are going to discuss on general characteristics of the compounds of the alkali metals. So general characteristics of alkali metal compounds: hydroxide and oxides. We are going to discuss about oxides, hydroxides, halides, salts of oxo-acids. So the first point will be oxide and hydroxides. So let's discuss oxide first. Okay. So all alkali metals form oxide in combustion, not in on combustion, in excess of air. So in presence of air or when we heat, they form oxides. Okay. So the first element of alkali metals, Li, it form Li2O oxide. Okay. And in rare case form peroxide, Li2O2. This is in very rare case. Now sodium, we know that it exists in peroxide. Okay, peroxide form. Peroxide. Okay, in peroxide. So plus in superoxide. In rare cases, this also in rare cases. NaO2. Okay, NaO2 superoxide. So the bigger element or the larger element, okay, such as potassium, rubidium, cesium, form superoxide. Okay, superoxide, MO2. Now lithium, okay, is small, that's why it form oxide, oxide, or we can say monoxide. Peroxide, sodium form peroxide because it is somewhat larger or larger than lithium. Now potassium, rubidium, cesium, they are larger. Okay, that is the reason why they form MO2. Okay, so smaller means they form small molecule. So this superoxide, peroxide, and even oxide, they are stable. Okay, the stability of the peroxide, okay, peroxide and superoxide is due to the stabilization of large anions, okay, anions by larger cation through lattice energy effects. So these larger cations, okay, K plus, K or Ru, okay, so they combine with oxygen, okay, anion, or to negative, okay, minus. So this larger one combine with two molecules of oxygen, okay, and form MO2. okay, that's why they are stable. Okay, and this Li, small Li, combine with oxygen to form monoxide. So two lithium combine with oxygen, okay, to form monoxide. Okay, so larger cation, larger anion, they form stable compound. Okay, so the combination of these anions and cations, okay, is also known as lattice energy. Okay, so the energy involved, okay, when anions and cations combine to form a compound, okay, something like this, okay, is known as lattice energy effects. Okay, that is in simple words. Okay, so similarly, I'm writing in short form. Similarly, small anion is stabilized, okay, by small cation through lattice energy effects. Small anion and small cation, they combine, okay, and then when they combine, energy is involved, okay, and that energy involved to make this compound, let's say Li2O, is known as lattice energy, okay, or energy effect. Let's see some more points. So this, the first one, Li2O, okay, and Na2O, they are colorless, okay, they are colorless when pure, okay, that means this oxide and peroxide, they are colorless when pure. This MO2 superoxide, they are yellow or orange, yellow or orange in color, okay. So this superoxide, they are also paramagnetic, okay, magnetic properties, paramagnetic. Now this sodium, okay, this sodium peroxide, okay, Na2O2, is used in inorganic chemistry. So this is used in inorganic chemistry for oxidizing, let's say S, okay, as oxidizing agent. Next one will be, let's take it as B, hydroxide. So the oxides we've discussed before, okay, those oxides, okay, are easily hydrolyzed, okay, by water to give hydroxide. So these oxides, they can be easily hydrolyzed by water to give hydroxide. M2O, this one, oxide, react with water molecule to give 2M plus 2OH minus. Now peroxide, M2O2, okay, where M is metal, combine with 2 moles of water to give 2M plus 2OH minus plus hydrogen peroxide. The third one, 2 moles of Mr2, that means superoxide, and 2 moles of water molecule combine to give 2M plus 2OH minus plus hydrogen peroxide plus oxygen. So they are hydrolyzed to give hydroxide. Okay, this OH. So these hydroxides, okay, these hydroxides obtained, okay, by hydrolysis, okay, are all crystalline solids, white, okay, white crystalline solid. They are all white crystalline solids. So this hydroxide, okay, of alkali metals, metal hydroxides dissolves freely in water. Okay, so they can be dissolved in water. So after dissolving, of much heat, okay, so when they are dissolved, they give off heat, okay, that means the reaction is exothermic, okay, heat is released due to intense hydration. Now let's see the last point. So this alkali, okay, metal hydroxides, the hydroxides of these alkali metals are the strongest base. Okay, in the previous videos we have discussed that alkali metals, they react with water, okay, and heat is released, okay, and it is also explosive also, okay. In the same way we can understand this alkali metal hydroxides, they dissolve in water, okay, with the evolution of heat, okay. So our second point is halides. So alkali metal halides, okay, alkali metal halides, this is HA, halides, symbol is MX, okay. So M stands for metal, X stands for chlorine, fluorine, bromine, and iodine. Okay, so these alkali metal halides, MX, X represent these, okay, elements. So they have high melting point, okay, and crystalline solid, okay. This crystalline solid, they are colorless, okay. So these metal halides or alkali metal halides are prepared by reaction of oxide, hydroxide, or carbonate with aqueous. I'm writing in short form, aqueous hydrohalic acid. So symbol is HX. Okay, let's see two example. Sodium hydroxide react with hydrohalic acid to give NaX, that means sodium halide, and water molecule. Now Li2O, lithium oxide, react with 2 moles of HX hydrohalic acid to give 2 LiX, so lithium halide and water molecule. So this is how they are prepared. Okay, now let's see another terms, okay, thermodynamic terms, okay, that is enthalpy of formation. So the symbol is delta FH. Okay, So in your textbook minus, okay, is given. So this minus means heat is evolved, okay, or they are negative, okay. Now let's see what does it means. So when two elements combine to form a compound, okay, the energy involved, okay, suppose A and B combine to form AB, the energy involved here will be the enthalpy of formation, okay, in forming this AB, okay. So the energy involved, let's see, A plus B give AB. So in this reaction, if heat is evolved, okay, or it is exothermic, then this delta HF value will be negative, okay, negative. I'm writing in short form negative, okay. And if suppose C plus D gives CD and heat is absorbed, so when heat is absorbed, delta HF or enthalpy of formation will be positive, okay. So we are going to talk about the enthalpy of formation of this alkali metal halides, okay. So let's see for with fluorine, okay. So how is the delta of formation, okay, enthalpy of formation with this fluorine? Let's see, LiF, NaF, KF, BF, CF, okay. So this enthalpy of formation is negative, okay, for LiF. So this LiF delta HF value is most negative, okay, most negative for LiF. So it decreases down the group, okay, decreases down the group, okay. So it decreases in this manner, okay. So this will be less negative, okay, this will be most negative, this less negative. Now let's see for other halides, okay, of alkali metals. So if we take X is equal to fluorine, bromine and iodine, fluorine, bromine and iodine, okay. So for simplicity, let's take it X, okay, is equal to LClBrI, okay, NaX, KX, RBX, X. So in this case, enthalpy of formation is, okay, negative. This is also negative, okay, negative, but it increases down the group, increases down the group, okay. So in this case, this one will be most negative, least negative, okay, this one. Now let's check for this one, fluorine, chlorine, bromine and iodine, okay. So LiF, LiCl, LiBe, Li. So this will be the delta HF. For LiF, both are small size, okay. This is the first element in the halogen, okay. This one also first element in the alkali metal. So they have the highest value, okay, most negative, okay, least negative, delta H, delta FH value or delta enthalpy of formation value. So it also shows that they are this alkali metal halides, okay, they are exothermic. Okay, exothermic means they release energy, okay, with when they combine with halogens. So all these halides are soluble in water except LiF, okay, and CSI. Okay, so this LiF, okay, is hardly soluble in water. Okay, since Li is the first element, F is also the first element, and they are very small. Okay, and the lattice energy is very high. Okay, because of that they are hardly soluble in water. So it becomes difficult for the water molecule to break this bond between Li and F. Now these two are the largest, okay, or bulky molecule. Okay, CSI, okay, CS is the last element, okay, in alkali metal, and I is the last one among the halogen. Okay, they have higher bigger size. Okay, and since they have bigger size, they have less hydration enthalpy, and because of this less hydration enthalpy, they are less soluble in water. So I hope these two are clear. Now let's see next one. Third one, salts of oxoacids. So before going to salts, okay, let's see oxoacids. So example of oxoacids are sulfuric acid, okay, hydrogen carbonate. Let's see the structure of sulfuric acid. SO OH. Okay, before going to structure, I'll write the chemical formula here. H2SO4 for sulfuric acid. For hydrogen carbonate, H2CO3, okay, for hydrogen carbonate. So H2S O4, 1 2 3 4. Now for hydrogen carbonate, CO OH. So CO3 1 2 3 H2. So oxoacids are those in which there is an oxo group present. Okay, this oxygen group 1 1 2 3. Okay, the double bond. Okay, this oxo group are the double bond, okay, attached to this main element, okay, or central metal, okay, or central ion. Okay, so they are called oxo and acids because this hydroxyl group can donate proton, okay, H plus ion. Okay, that's why they are acid. Okay, so we all know that acids are those which can donate proton. Okay, so they are called oxoacids. Okay, now salts of oxoacids. So we are discussing in terms of alkali metals. Okay, so alkali metals forms salts, okay, with all the oxoacids. I'm writing in short form. Okay, so alkali metals, they can form salts with these oxoacids. Okay, so example are carbonates, okay, M2CO3, hydrogen carbonate, and sulfates. Let's see two reactions, Na plus H2SO4. So it gives Na2. Okay, let's balance this one. Na2 SO4 plus H2. So this is the sol. Okay, sol of oxoacid. Okay, so the name of this chemical will be sodium sulfate. Next one, 2Na plus hydrogen carbonate to give Na2CO3. This is sol of oxoacid. Okay, plus H2. This is sodium carbonate. So in these reactions they form salts, okay, and hydrogen is released. Okay, so in this case this will be the positive part, this will be the negative part. Okay, positive, negative part. So it, since Na2, okay, this will be SO4 2 minus, okay, Na2 plus, two plus, 2 minus. So these salts, okay, salts of oxoacids, they are all soluble in water, and thermally stable. There is some exception, except Li2CO3 and lithium hydrogen carbonate. You all know this because this Li is very small, okay, and it is also polarizing also. Okay, so as the electropositive, okay, so alkali metal, they are electropositive. We have discussed before though that also increases down the group stability of carbonates, and hydrogen carbonate, I'm writing issue from hydrogen carbonate, increases. Okay, so as we move down the group, electropositive character increases, and because of electropositive character increases, stability of these carbonates and hydrogen carbonates. Okay, that means salts of alkali metals, their stability increases down the group. Okay, lithium has a smaller size. Okay, that means it will be least stable. Okay, and that's why they are not soluble in water, and they are thermally not stable.